Okay. In this video, I want to continue talking about unions and intersections. And this time I want to talk about unions and intersections of more than two sets. We're going to show this holds in depth once we learn something called induction. But we can start talking about it now just to explore what these sets look like. And we have a little bit of notation. And if you look at it, it might remind you of that summation notation here. So what this means is we're taking the union of sets A1 through AN. So it looks like A1 union A2 union A3, A4, whatever, all the way up to AN, depending on what N is. And its definition reads as follows. It's all elements X such that there is an index I, so that your element is an element of AI. So you can find an AI there. And actually I wrote union twice. This one means to be the intersection. So let me change this. This shouldn't be a union. This should be an intersection from I equals 1 to N of AI. And for an intersection, it needs to be in all of them. So it can't just be in one. It needs to be in all. So it's for all I. And this one looks very similar, except it is A1 intersect A2, intersect all the way to intersect AN. Let me give you guys a little small example just with three sets. So let's say that A1 is going to be the set 1, 2, 3, 4. A2 is going to be the set 2, 3, 4, 5. And A3 is going to be the set 3, 4, 5, 6. So let's say we have those. I'm just going to do this down here just to make a little bit of room. Then let's take the union of those three sets, AI. Well, the union is going to be all the elements that are in any of these sets. So what does that mean? There is an I, 1, 2, or 3, so that that element is in one of them. So, for example, 1 is going to be in our indexed union because 1 is in A1. There is an I, that I is 1. It's in A1. 2 is also in A1. It's in A2 too, but remember for unions, it just has to be in 1, at least 1. 3 is in A1. 4 is in A1. 5 isn't in A1, but the I that exists so that 5 is in AI is 2. 5 is in A2. So 5 is in here. And finally, 6 is in here. So the union of these three sets is 1, 2, 3, 4, 5, and 6. The intersection works similarly, but instead of there exists, it needs to be in all of the sets. So the intersection of these three sets is going to be, well, is 1 in all of these sets? Well, no. 1 is only in A1. It's not in A2. I don't even need to look at A3 because I know it's not in A2. What about 2? 2 is in A1. 2 is in A2, but 2 isn't in A3. So it's not true for all I. Remember, for intersections, it needs to be true for all. 3, on the other hand, 3 is in A1, A2, and A3. So we get 3 in our set. 4, similarly, is in our set. 5 is not because 5 is not in A1. And 6 is not because 6 is not in A1. So we only have 3 and 4. And that is how these indexed unions and indexed intersections behave. A lot of times, I will say, your AIs, I don't want to use that, I want to use a pen. In a lot of cases, these are given by a formula depending on I. And we'll do some examples where we'll see that. And it is possible for these sets to have infinitely many elements. In fact, the examples we're going to do will have these sets here being intervals of real numbers. Okay. So, there's nothing special about having a finite union or a finite intersection where you're taking the union and intersection of finitely many sets. You could do it for infinitely many sets as well. So you could go through all of your counting numbers ranging from 1 up to infinity. And so that reads like this. It's the union of AIs from 1 to infinity. All elements x such that there is an index I where x is in one of the AIs. So same idea, but instead of having a finite number of sets, you have an infinite number of sets. And the same thing with the intersection. Instead of there exists, it needs to be in all of them. So you might see the notation from 1 to infinity or from whatever to infinity. Another notation you might see is I is an element of the natural numbers. So that's another way of writing this here. And similarly, for the intersection, same idea. Just another way of writing the index. And again, we're not going to touch on this too much, but the indexing set doesn't even have to be a counting set. It doesn't have to be the natural numbers. You could have an indexing set be, say, the real numbers or whatever. So just know that this kind of idea holds for any indexing set, not just the natural numbers or subsets of it, which is, oh, it's pretty cool. This is kind of a difficult concept, so I really want to do a few examples, and hopefully that will give you an idea of what's going on. So here's an example where I want to calculate both a finite union and a finite intersection, and an infinite union and an infinite intersection. Now, what I mean here, this is interval notation. So what this means, this is all x such that, well, x is between 1 over I, but not including 1 over I, so it has to be bigger than 1 over I, but less than I plus 1 over I. So that's what I mean by that set there. It's the interval from 1 over I, whatever I is, to I plus 1 over I. Or if you like, you could rearrange this. I plus 1 over I is the same thing as I over I plus 1 over I, which is, of course, well, I over I is 1, and we're left with a 1 over I. And we're thinking of I as some index number. So let's say if I was 2, this would be the interval from 1 over 2, so a half, to 1 plus 1 over 2, so a half, to 3 over 2. And sometimes it's a good idea to draw these on the number line. So let's do a little number line here to help us out. So here's 0. Let's have 1 be here. And here's a half. I don't know where I wrote 3. I should write 1. 1. Here's a half. Let's have 3 halves be here. And let's go all the way up to 2. Why not? And that, of course, keeps going in both directions. So let me write down what A2 is. So A2 is going to be the interval from 1/2 to, well, 2 plus 1 is 3/2, so 3/2. So A2, which I'll do in red here, that's all numbers here. There's A2. Let's explore another one. Let's explore, how about A1? Let's do A1. I'll do A1 in blue. So A1 is going to be everything from 1/1, which is 1, to 1 plus 1, which is 2/1. And you can simplify this, of course, to the interval from 1 to 2. So this interval here, this is A1. All the numbers between 1 and 2. Not including 1 and 2, but all the real numbers in here. A2 is all the real numbers between 1/2 and 3/2. Similarly, let's do A3. That's everything from 1/3 to 4/3. So 1/3 is about there. 4/3 is about, there's 1/2, so 4/3 would be about here. So that is, I'll mark them in, that's 1/3, that's 4/3. So that's A3. So maybe try and mark A4 and A5 on this number line. And then we can do at least the first two. We can see what that set is going to be. Okay, now that we're back, I'll do A4 in yellow. So A4 is going to be from 1/4 to 5/4, or 1 1/4. So that's going to be here to here, say. So that is 1/4 to 5/4. There's A4, and the only color I have left is black, so A5 will be from 1/5 to 6/5, which is about here. Again, this is just a sketch, of course, but I think it'll give the right idea. So A5 is all of that. Now, let's think definition-wise what the union from I equals 1 to 5 of these AIs is. Well, remember, the union is all the points that exist in at least one of these indexed sets. There exists one set, or more than one set, of course, that it's a member of. So if we think about it, well, all of these points that got highlighted from 1/5 all the way to 2, they're in one of these sets. All the points from 1/5 to 6/5 are in A5, from 1/4 to 5/4 is A4, 1/3 to 4/3 is A3, 1/2 to 3/2 is A2, and 1 to 2 is A1. So all of these points here are in at least one set. So this entire interval is going to be everything from 1/5 all the way to 2. And again, not including these endpoints. If we did want to include the endpoints, I'm just going to draw these in, or maybe I'll make a note. If we did want to include the endpoints, we'd use square brackets. If we want to include the numbers 1/5 and 2, we would use square brackets. But this just means right up to 1/5, but not including it, and right up to 2, but not including it. Now that you have that idea, see if you yourself can work out what the intersection of those, or I'll do this in black. What is the intersection of those sets from 1 to 5? Pause the video now. Have a think about it. Remember, it has to be in all sets. That's the key. Okay, now that you're back, if we think about it, the only region that is covered by all 5 of these sets is this region here, from 1 to 6/5. That region, if you check, is overlapped by every one of these sets. So the intersection, the indexed intersection of these sets from 1 to 5 is from 1 to 6/5. It's the bit that is covered by all 5 sets. Now that they're done, let's look at the infinite version. This is a little bit harder. Kind of what we're going to do is we're going to think of, and this is going to be loose notation, but it's worthwhile. Let me scroll up here. We're going to think about what is, and this is kind of not a real set, but we're thinking of what is A infinity. If we plug in I equals infinity, or if you've taken calculus and understand limits, what we're doing is we're taking the limit as I approaches infinity and seeing what set that would give. So if we could plug in infinity, what would that look like? Well, A infinity would be the set, or I should say the interval, since we're talking about intervals, the interval from 1 over infinity, 1 over a really, really big number, to, I'm going to write it as 1 plus 1 over infinity. So what is that? Well, 1 over infinity, you can check if you plug in really big denominators, the numbers get really small. So if our denominator is big, our number is small. So this goes to 0. 1 over infinity is basically 0. And then we have 1 plus 1 over infinity, so that's 1 plus 0, which is 1. So if we think about this, let me scroll back up, and I'll do this in a different color or a dotted color or something. I'll put this on our number line that we had. So there's our number line. And let's do this, I don't know, in squiggly red. That will do. So A infinity, if you will, is everything from 0 all the way to 1. I'll use some dotted brackets here. So it's all of that. And if we think about it, if we see the pattern that's going on, we can see that these sets, here's A1, A2 gets shifted towards 0, A3 gets shifted towards 0, A4 gets shifted towards 0, A5 gets shifted towards 0, and that idea will keep happening. We'll have an interval of length 1 that gets closer and closer to 0 on the left. So this is basically as close as we get. This is our, if you like, A infinity. So we kind of have all of these sets, and this is the limiting set. So if we think about it, what is the union and intersection of all of these? So let's scroll up just a little bit. I want to keep this here. So let's do the infinite union first. So I can write it like this, of the AIs. Well, again, that's going to be all of the numbers that are in any set. So you can imagine, well, we have everything from 2 all the way down. So we have from 2 to 1 in A1, and then we gather some new stuff up to a half in A2, and then A3 takes us to a third, A4 takes us to a fourth, A5 takes us to a fifth. And remember, it's a union, so it just has to be in 1. So we can just say what we're adding by keeping on going. A sixth would take us to a sixth, and as we keep on going, we get all the way to, but not including, 0. So the union has everything from 0 to 2, but not including the endpoints, of course. So that is the infinite union. And just to see the other notation, it means the exact same thing. But the infinite intersection, which I'll write like that, or I should say is an element of. Just to be clear, this I equals 1 to infinity is the same thing as I is an element of the natural numbers. They mean the same thing. Okay, so we have this infinite intersection of these AIs. Well, let's ask, what elements are in all sets? And maybe pause the video now and think about that yourself. Using this idea that we talked about here with the number line, think about if you can determine which elements are in all sets. Okay, now that you're back, well, if we think about it, we're going to go almost the opposite way. So let's think about what we have already, the overlap of all sets from 1 to 5. That's these guys here. As we keep going, A6 would take us right to 7/6 and then 8/7 for A7, and we keep going all the way, and we get closer and closer to 1. So the only element that looks like it could possibly be in our intersection is indeed 1. So the question is 1 in our intersection? And the answer is yes. So the final answer for this one is just the number 1. And let me explain why. Let me show you why 1 isn't in anything else. So consider the interval 1 over I to 1 plus 1 over I. So for any I, for any integer that you like, or I should say natural number that you like, 1 is definitely greater than 1 over I. That bit's easy. But it's also less than 1 plus 1 over I. I'll write it like that. Remember, we're thinking of A infinity just as a little heuristic. But all of these sets are A some natural number. So AI. Remember, I is a natural number. So this here, it approaches 0. But never is 0. So we have 1 is going to be less than 1 plus a tiny bit. This gets tinier and tinier, but it's never 0. We can't actually plug in infinity. It's just a little heuristic to say what it approaches. So we do indeed have 1 in our infinite intersection. So that is the idea of indexed unions and indexed intersections. We're We'll continue on in the next video with a few other set topics.